Hi, my name is Landon Clark. I'm a PhD student in the Intelligent Robotic Arms Lab. My advisor is Dr. Bayun Shi. I'm here today to talk about my research in fault tolerance workspace approximation for redundant robots experiencing locked joint failures. A redundant robot is a robot with a higher degree of freedoms. We can typically think of this as the number of joints that the robot has, and this degree of freedom is higher than the number of degrees of freedom required to complete a given task. So for example, if our task is in the XYZ task space, then a 4-joint robot would be redundant. Now, fault tolerance is our ability to guarantee that given an arbitrary joint failure, we're able to reach some point in our task space despite this failure. So our research here is looking to analyze what this task space is and figure out maybe some other properties about it. Our motivation behind this research, this typically applies to robots in very remote environments, such as a Mars rover, or in dangerous environments, such as something like nuclear waste removal. Now, our first main concept here, we're looking at this self-motion manifold. This is essentially a shape in joint space where at any point along this shape, we are staying on the same exact end effector location. So even though we change our configuration in general, we aren't moving at the very end of our arm. Now, when we calculate this, we find our null space vector, we move along this vector, and essentially we keep this stepping and updating process where we step along the null space vector and then we update and find a new null space vector. As we can see, these shapes can get pretty complicated pretty quickly. Now, for a simpler case, we can think of these artificial joint limits that we're going to introduce here a little bit more simply with the figure to the right, where we can place these bounding boxes around a self-motion manifold. So again, given the figure to the right, we see that the self-motion manifold for B is inside of that middle box. Essentially what that's saying is if we stay inside, if joint 2 and joint 3 stay inside of those values, then we will be able to reach point B. Now our fault tolerant workspace, this is the reachable workspace given our artificial joint limits that we've defined by these bounding boxes. So this is going to be a little bit more complex of a computation. We're going to consider perhaps essentially an infinite number of points, but we can sample that down and with some sort of resolution, we can figure out a basic idea of our fault tolerant workspace. And a good example of this would be a paper that we are working on improving. They apply a sampling-based approach to reduce the complexity that's typically required for the fault tolerant workspace calculation of a high degree of freedom robots. Doesn't give you the ability to determine whether or not a specific orientation was in the fault tolerant workspace. So real quick, diving into what we have so far, we have essentially some very preliminary work here that we have been able to map out for the time being, at least a 3R fault tolerant workspace given the following joint limits. As we see, the ground truth is on the right and our work is on the left. So at this point, our position calculations seem to be on point. Now our future work, again, we're looking to not only determine whether or not a position lies in our workspace, but also if our whole 60 point orientation values, if all 3 of these, or sorry, or 6 of these fall into our fault tolerant workspace. We're also looking to generally improve how we represent orientation, make it a little bit more intuitive, as well as applying perhaps some machine learning algorithms to speed up these prediction processes. Now, specifically on the sampling process, one idea right now is the adaptive sampling. So what we do is we find these workspace values at a given grid center. We find how the nearby points relate to other nearby points. And if there's a large difference between them, then we would decrease the sampling size, and vice versa. If there's a small difference between these points, we would increase the sampling size. Essentially, what we're saying here is if a lot of close by points have big differences, that probably means that we need to be very careful about how we're sampling and make sure to note these differences. Otherwise, if these differences are smaller, then we can assume that one point has a pretty good estimation for the nearby points. Now for our orientation workspace, we're looking to use a spherical surface. So this should just be a little bit more intuitive from the way we traditionally think of the orientation of the robot to then our mathematical representation of orientation. And that's about it. Here are some of our early papers that we've looked at. Yeah, that's it. So thank you for watching. Have a good day.